We talk endlessly about energy transition, geopolitical shifts, but maybe the single biggest material threat facing loads of regions today is something you can actually see and touch: water scarcity.
Absolutely.
For some countries, it's really moving beyond just a management issue. It's becoming, well, an existential challenge.
It truly is. And Iran, it really stands out when you look at the nations facing the most acute stress.
Yeah.
I mean, it's the 17th most populated country, but it ranks in the top 10 globally for water stress. It's like a perfect storm brewing.
Okay.
Sources point to, dramatic climate change, rapidly increasing demand, domestic, industrial, and frankly, decades of maybe less than ideal resource management. It's all hitting at once.
And those projections really spell out why we'd call it an emergency, right?
Right.
There's this threshold for critical water scarcity. I think it's 1,000 cubic meters of renewable water per person per year.
Yeah.
Below that, life gets fundamentally unsustainable.
That's the crisis threshold, yeah.
And Iran was already projected to drop to just 800 cubic meters per capita back in 2021. That shortfall is exactly why experts are warning quite starkly that this whole crisis could potentially make huge parts of the country just uninhabitable.
Yeah, this isn't some far-off 2050 problem. This is happening right now.
So, okay, let's unpack this massive challenge. When the stakes are that high, you have to look at pretty radical solutions.
You really do.
Today, we're diving into one proposal that's incredibly ambitious, maybe even radical. Our deep dive is focused entirely on a specific study. The full title is Securing Future Water Supply for Iran Through 100% Renewable Energy-Powered Desalination.
Right.
Our mission here is to figure out if this huge, complex, 100% renewable fix is actually possible technically and, crucially, if it makes any economic sense.
And the headline finding, if you need it up front, the study found that, yes, a 100% renewable energy system can reliably secure Iran's future water needs.
Wow.
And what's more, it found this green approach could actually achieve costs competitive with the fossil fuel desalination plants running in Iran right now.
Yeah.
That's pretty huge optimistic finding.
That really is the finding that opens up this whole conversation. But I think to really get a feel for the scale of the proposed solution, we need to grasp just how deep this crisis runs first.
Okay, let's start with some context then. We mentioned water stress. Scientifically, high stress happens when a country withdraws more than 40% of its renewable water resources.
40%.
Yeah, cross that line. And it basically means you're dipping into fossil groundwater. That's water that just won't replenish on any human timescale.
And Iran's been hitting that fossil water hard. The depletion numbers, they're almost hard to believe. Research shows between 2003 and 2012, Iran saw the biggest groundwater loss in the whole Middle East. Something like 25 gigatons, give or take 3, every single year.
It's a massive amount. And that kind of over-extraction, it doesn't just mean future scarcity, it's causing physical damage right now.
Like what?
Well, in the greater Tehran area, which is obviously densely populated, we're seeing serious land subsidence. The ground is literally sinking several centimeters a year. And that's not just a cosmetic issue. It damages crucial infrastructure, roads, gas lines, big buildings. It's a real physical threat.
And beyond the infrastructure, there's the ecological damage.
Wow, absolutely. The environmental collapse is maybe the most visible part. Iconic places, crucial water bodies like Lake Urmia.
The huge salt lake.
Exactly. That one and Lake Human, they're shrinking fast or have basically dried up entirely. That changes the whole regional climate, destroys unique ecosystems. It's devastating.
What's worrying is that some of the past government actions, like building lots of large dams, which you'd think would help manage water, well, they've been criticized for maybe making the crisis worse.
Yeah, many policy experts argue just that. Dams are useful for energy and flood control, sure, but they can block the natural water flow that those downstream wetlands and lakes desperately need.
Right.
Plus, they can create this sort of illusion of abundance in certain areas, which encourages unsustainable development nearby, only to lead to worse depletion down the line. It's a classic unintended consequence.
So, if the inland water sources, both on the surface and deep underground, are collapsing, the obvious place to turn is to the ocean. We know there are already big plans for massive water transfer projects, basically moving desalinated water from the Persian Gulf and the Gulf of Oman inland.
That's right. The aim is to supply something like 47 million people in those central, really water-stressed provinces.
What's the current desalination capacity like?
Well, back in 2015, the national capacity was already pretty significant, over 800,000 cubic meters a day. But and this is key, about 62% of that was going to industry.
Ah, okay. Not domestic use.
Mostly not. So to meet the huge domestic and farming needs for a population this size, you need an absolutely radical increase in capacity, and that demands equally massive, reliable power generation.
Which brings us perfectly back to the core of this deep dive.
Right.
The 100% renewable energy system proposal. This study didn't just tweak things, it modeled a really bold 2030 scenario. They called it optimistic, where Iran basically adopts a fully integrated, 100% renewable system designed specifically to meet all the country's projected water demand. No fossil fuels involved. Conceptually, it aligns with those COP21 net zero goals.
And the complexity here is really interesting. To get that 100% reliability without fossil fuels, the model found the best mix, the optimal hybrid RES needed four main things.
Okay, what are they?
Solar PV, both fixed tilt and the single axis tracking kind, wind power, battery storage, obviously, and also power to gas plants.
Power to gas. Okay, we'll circle back to that. But first, let's talk scale, because the numbers involved here are just staggering. What size of infrastructure are we actually talking about needing by 2030?
The required capacity is, it's eye-opening. The model projects that to meet demand, the total desalination capacity needed by 2030 is 199 million cubic meters per day.
199 million cubic meters daily.
Daily. And to power that reliably with renewables, you need huge deployment. We're talking about installing 561 gigawatts of total PV capacity, mostly the single-axis tracking type.
561 gigawatts. Okay, just to put that in perspective for you listening. The entire current electricity generation capacity of a major economy like, say, Germany or France is usually around 100 to 200 gigawatts. So this is talking about building maybe 2 or 3 times that much capacity just in solar, just in Iran, just to power desalination. That's enormous.
It's a total scale shift.
Right.
And it needs massive storage to back it up. The model calls for installing 360 terawatt hours of battery capacity.
360 terawatt hours.
Which is where that power to gas component, PTG, becomes absolutely essential.
Right. Let's pause there. PTG, power to gas, might not be a familiar term for everyone. How does it fit into this 100% renewable picture? What's its job?
That's a good question. PTG is basically the system's main flexibility provider, especially for longer-term storage. It works by taking excess electricity power from the wind or solar farms when generation is high but demand is low.
Okay, surplus power.
Exactly. It uses that surplus power to produce hydrogen or maybe synthetic methane through electrolysis. This gas is then stored. And then, when the sun isn't shining or the wind isn't blowing, say, during seasonal low points or long cloudy spells, you can feed that stored gas back into the system, often using gas turbines, to generate electricity again.
Ah, so it's like the seasonal storage solution, filling the gaps that maybe batteries alone can't cover for long periods?
Precisely. The study showed PTG cuts down the amount of wasted or curtailed renewable energy by a huge 75%. And crucially, it ends up providing up to 15% of the total energy demand itself.
Okay.
Which means you don't have to overbuild the PV and batteries quite as much just to cover those tricky reliability gaps. It optimizes the whole system.
Makes sense. And sticking with constraints for a moment, this study only looked at the Persian Gulf and the Gulf of Oman for water sources, right?
Yeah.
Why not other big water bodies like the Caspian Sea?
Yeah, that was an environmental constraint built into the model. The Caspian Sea, it's technically a saline lake, not an open ocean. Using a body like that for massive desalination and then pumping concentrated brine back into it, well, that could severely damage its unique ecosystem. The Persian Gulf and Gulf of Oman, being open oceanic systems, are considered better able to handle brine discharge, though it's still a major, major concern we need to talk about.
Definitely. Okay, let's pivot to the big question. Cost. This is where feasibility really gets tested. Can Iran actually afford this massive undertaking? This is where the study delivered its key economic insight.
Right. They calculated the levelized cost of water, the LCOW. Just for clarity, LCOW is the average cost to produce 1 cubic meter of water over the whole project's life, factoring in everything, building it, running it, the energy.
Okay, the all-in cost per cubic meter. What did they find?
The study found the LCOW for this 100% renewable system ranges from about 1.0 euro per cubic meter up to 3.0 euros. But it was mostly concentrated between 1.0 and 2.5 euros per cubic meter.
And what about the cost of the electricity itself, the LCOE?
The levelized cost of electricity for the whole renewable system, solar, wind, batteries, PTG, was found to be between 0.06 euros per kilowatt hour and 0.11 euros per kilowatt hour. Pretty competitive for renewables.
So let's bring that water cost, the LCOW range of 1.0 to 2.5 euros, back to the real world. How does that stack up against what Iran pays now using fossil fuels for desalination?
Well, currently, the reported cost just for water production at a typical fossil-fueled SWRO plant, that's seawater reverse osmosis, just at the plant gate, no transport costs included, is around 0.70 euros per cubic meter.
Okay, so 70 cents.
Roughly. Now, the study found that the full renewable system right there on the coast, including the storage and the initial bit of transportation infrastructure, comes in between 1.0 and 1.50 euros per cubic meter.
Ah, so in that range, it's actually quite competitive, especially considering.
Exactly. Especially considering renewable costs are still dropping globally, it makes the economic viability look really quite strong.
But that range, 1 euro to 2.5 euros, is still generally at the higher end or maybe a bit above the typical global average for desalinated water, which is often quoted around 0.70 to 2.0 euros per cubic meter. If the energy cost, the LCOE, is low, what's pushing the water cost up, specifically in Iran's case?
This is maybe the most critical finding, the real aha moment from this study. The cost driver isn't primarily the solar panels or the batteries. It's almost entirely down to geography.
Geography, how?
The single biggest factor inflating the LCOW above the global average is the sheer amount of energy needed for water pumping.
Just moving the water inland. How much does that contribute?
It's huge. The study shows that the energy used just for pumping the desalinated water inland makes up approximately 38% of the total levelized cost of water in Iran.
38%,
Yeah.
just for pumping.
Yeah. Now, compare that to the global average, where pumping energy usually only accounts for about 16% of the total LCOW. You can see just how significant that geographical penalty is for Iran.
That's fascinating. So geography is a bigger hurdle than the tech or the energy supply itself. We're talking huge distances, vertically and horizontally, to get that water to the dry central areas. Can you give us a sense of the kind of elevation involved?
The challenge is literally steep. Some projects mentioned in the source material require pumping water up elevations of 1,700 meters.
Wow.
And for supplying certain mining operations, potentially up to 2,700 meters elevation gain.
That's, what, nearly 9,000 feet?
It's like lifting water higher than two huge skyscrapers stacked up. The infrastructure needed for that, the pipes, the pumping stations, and the sustained energy to run them, it's enormous.
And since you have to build all that infrastructure first, where's the initial money, the capital expenditure, going?
Good question. If you break down the costs, the total upfront capital spending, the CapEx, makes up about 64% of the final LCOW. And within that CapEx, the single biggest chunk, it's the vertical transportation infrastructure. Building all those pipes, pumps, and stations needed to lift the water up those mountains accounts for a full 25% of the total capital cost.
So it really confirms that the biggest expense is basically fighting gravity.
That's a good way to put it.
So, okay, the cost seems viable, especially compared to alternatives, but this geographical constraint is massive. What are the broader takeaways? What do policymakers need to keep in mind if they pursue this?
Well, the study really hammers this point home. Desalination, even on this scale, cannot be a silver bullet used in isolation.
Right.
This huge tech investment has to go hand in hand with really aggressive water management and efficiency improvements, especially in agriculture.
Why agriculture specifically?
Because currently, farming accounts for a staggering 90% of Iran's total water demand. 90%. If you don't fix the leaks, the inefficient irrigation methods, no amount of new desalinated water is ever going to be enough. You have to tackle demand too.
That makes sense. We also need to address the big environmental elephant in the room with desalination, even renewably powered. The brine. The leftover salty water.
Absolutely. This is a major, major concern. The Persian Gulf and the Gulf of Oman are already pretty stressed ecosystems. And the Gulf countries, collectively, already dump over half of the world's total desalination brine discharge into those waters.
Half the world's total.
Yeah. So if Iran ramps up its capacity to that projected 199 million cubic meters per day, the extra salinity, potentially temperature changes too, it could cause a really significant ecological problem if it's not managed very carefully.
What did the study suggest for managing that massive amount of brine? Are there solutions?
They mention a few potential strategies. The most straightforward one is dilution, mixing the super concentrated brine with other water sources, like treated wastewater perhaps, before discharging it, just to lower the concentration.
All right.
On the more cutting-edge side, still very much developing, is the idea of brine mining. trying to extract valuable minerals from the brine itself.
Like what?
Things like lithium, magnesium, other scarce metals. If you could perfect that, you could potentially turn a costly waste stream into an economic resource. But, that technology is still quite nascent, not ready for prime time at this scale yet.
Right. And finally, like any big modeling study, this one identified areas where more research is needed to make the picture clearer.
Yeah.
What were the main knowledge gaps?
They pointed out a couple of key things. First, they really need better updated Iran-specific data on water transportation costs. Things like, what are the local soil conditions like for laying pipe? How difficult is the terrain, really? What's the state of the existing electrical grid to support all this?
Local realities, basically.
Exactly. And second, and this is crucial, they need to model the desalination demand after assuming those aggressive water management strategies we talked about, like major upgrades to irrigation efficiency nationwide, are fully put in place.
Because that could potentially reduce the total amount of desalinated water needed.
Potentially significantly. If you manage demand better first, maybe you don't need 199 million cubic meters per day. Maybe it's less, which would make the whole project smaller, cheaper, and have less environmental impact. That needs proper modeling.
Okay, let's try and pull together the main threads from our deep dive into securing future water supply for Iran through 100% renewable energy-powered desalination.
I think the big takeaway is the technology seems ready, and the economics look surprisingly competitive. A robust, hybrid, 100% renewable system, solar, wind, batteries, power to gas, it can reliably meet Iran's huge projected water needs by 2030.
Yeah.
And it can offer prices that are becoming comparable to or even better than sticking with the existing polluting fossil fuel systems, especially as green tech costs keep falling.
But, and it's a big but, the essential realization from this study seems to be that while technology can solve the energy problem, it doesn't really solve the gravity problem.
Exactly.
The massive energy costs and the huge capital costs just to pump all that water from the coast way up inland over steep mountains. That remains the single biggest economic and engineering hurdle.
Which does raise a really fundamental, kind of provocative question, I think. Not just for Iran, but for any country facing severe water stress near its coast, but far from its people.
Right.
Does a country's basic, unchangeable physical geography, its mountains, its sheer elevation changes, ultimately put a hard limit on its ability to achieve total water independence? Regardless of how advanced or cheap our green technology gets, can we engineer our way around gravity on that scale affordably?
That's a really powerful challenge. Nature versus engineering and the economics binding them together. That was our deep dive into the findings of securing future water supply for Iran through 100% renewable energy-powered desalination. We definitely encourage you to look into the source material and ponder those geographic constraints for yourself.